Okay, so in this short note, we're going to talk about pure states and unitary evolution. So let's consider a density matrix, which is written as rho, and rho will be sum over I, and this is the probability pi. So sum of pi is equal to 1, and then this is the outer product of state psi I with itself. So this is known as outer product. Now the system is said to be in a pure state if all pi's, that is all of these, are 0 except 1. So only one of them is non-zero, and hence since it has to satisfy sigma pi equal to 1, it's just 1. So then that is what we call as a pure state, and it is written as rho pure psi outer product with psi. Now if we take the square of rho pure, we get this, and then again we get the same thing, but noting that psi is normalized, so this is equal to 1, we get psi psi is equal to 1, so rho pure square is equal to rho pure, and then you can take trace on both sides to establish that trace of rho square pure is equal to trace rho pure, and this is a property of a pure state. In fact, if you want to check whether the state is pure or mixed, you just need to note the violation of trace rho square from trace rho, and trace rho is normalized to 1. So the violation of trace rho square from 1 in some sense gives you a measure of how mixed the state is, right? Now one of the important things about pure states, which is very important for physics, is that pure states remain pure under unitary transformations, and we will now prove this. So under unitary transformation, what happens is a state psi will go to u psi, where u is a unitary operator. What do we mean by unitary operator? We mean that u dagger u is equal to identity matrix. That is the definition of the unitary operator. So psi will be psi, which was given by this, will now become u psi, and and the outer product with this thing, which is given by this, where this is u dagger, because when you go from a bra and a ket, there's a transpose conjugate involved. So aij has to be taken like this, and then you have to do a complex conjugate of that. So this is what we get. Now this means that rho evolved is just given by u times, this is nothing but rho start, that is the state we density matrix we started with, and then u dagger. Now if we square this, we get u density matrix at the start, u dagger, and then the same thing, right? But I already told you that u dagger u or u dagger u is equal to identity, so this just gives me this. And then we can take trace on both sides to get trace rho evolved square is equal to trace start square. Now this is because I can now, when I take the trace of this quantity, I can use cyclicity of a trace, and this can be just written equal to trace of rho start square u dagger u, and this is identity. So this is what you get, and that is equal to 1. So this is a proof that if you start with a density matrix or density operator rho and evolve it by some unitary transformation, you still have retained this property. So a pure state will remain pure. And usually the unitary operator is given by e exponential of minus h hat t, where h is the Hamiltonian. And you can check that this is indeed true, that this is identity. Thank you.